All right, guys, here are the notes for Chapter 6, Section 1. Chapter 6 is all about solving systems of equations. I know we know how to solve an equation, so in Chapter 6, we start dealing with more than one equation at a time, called a system of equations, and finding a solution for that system. So, let's get started. Solving a system of equations. Let's start with the solution to an equation. Now, the equations we're talking about in Chapter 6, as they were in Chapter 5, are equations that have two variables in them, predominantly x and y, right? And the solution to an equation with two variables is an ordered pair that makes the equation true. All right? And I did a little example here. I have an ordered pair and I have an equation. And I want to know, is this ordered pair a solution to this equation? And of course, you can tell if it's a solution by substituting the x value in for x and the y value in for y. So that might look like this. And we're saying, is that true? So we'd go ahead and we'd simplify the right side. And in fact, we find out it is true. Yes, that ordered pair is a solution to that equation. Right? So in Chapter 6, though, we're not going to be dealing with the solution to one equation. We're going to be dealing with the solution to a system of equations. So what is a system of equations? Well, a system is a set of equations, or we might do inequalities, joined by the word and. That just means that both things have to be true, that together describe a single situation. So the bottom line is this, you guys. We're going to have two equations generally with two variables in them, and we need a solution for both equations. As it says here, for us this will generally mean two equations that each contain two variables, though a system of equations could be as many equations as you want with as many variables as you need to solve it. Here I have a simple example of a situation that might lead to two equations. A second grade class has 23 students. There are 5 more boys than girls in the class. How many boys and how many girls are in the class? Well, the first thing I would do for this situation is I would set up two variables. My variables might be x and y. And, you know, like we did back in Chapter 2 when we set up variables to represent stuff, in general, the variables need to represent the answer to the question. So the question is, how many boys and how many girls are in the class? I'm going to have x be the number of boys in class, and we'll have y be the number of girls in class. And so I have underlined what I believe the two equations might be. The red one is that the class has 23 students. So that would lead me to the equation x plus y is equal to 23. Or the number of boys plus the number of girls equals 23, right? And then the blue equation says that there are 5 more boys than girls. So the number of boys would be equal to the number of girls. Now, are they equal? Well, no, they're not equal. There's 5 more boys. So that means the number of boys would equal the number of girls plus 5. now they'd be equal if we added 5 to the number of girls. All right, this is an example of two equations. This little bracket thingy means and. It means the first equation and the second equation both have to be true. We would be looking for a solution, an ordered pair, that you could put in for x and y that would make both equations true at the same time. All right, that is just an example of a system of equations. Two equations with two variables. We're not actually going to solve it, though you probably could pretty easily. How do you solve a system of equations? Well, in this chapter, we're going to learn 3 ways to solve a system of equations. Today we'll do what's called the graphing method. And then I think tomorrow we will do the substitution method. And then the next day or two we will do the elimination method. So 3 different methods that really do the same thing. They all solve a system of equations. Why do you need 3 methods? Well, maybe technically you don't. But what we would hope to do at some point is determine, when we have a system of equations, which method is the best one to use. And that might depend on what type of problem it is. Oops. So, solving a system by the graphing method. So the first thing we're going to learn is how to take a system of equations and solve it by graphing. We just got done with a whole chapter on graphing equations, so I'm hoping this is not too tough. I have a few reminders for you about graphing. Equations can be graphed by putting the equation into... I'm going to fix the board real quick. So you can take an equation and graph it by putting the equation into slope-intercept form. And of course, we all know that's when the equation looks like y equals mx plus b. Right? When equations are in that form, they're very easy to graph. The ordered pairs that are on the line are solutions to the equation for that line. Remember how I always say this is what a graph is. A graph is a picture of the answers to the equation. Well, the solution to a system of equations would be any ordered pair that is on both lines. All right? If we are given 2 equations, we're going to end up graphing 2 lines, and we're going to look for an ordered pair that is a solution for both. So up here, I have the directions of how to solve a system by graphing. The first step is to graph each equation on the same coordinate plane, something we practiced quite a bit last chapter. The second step would be to name the point where the lines intersect each other. Since this is a point that is on both lines, it must be a solution, the board is broken again, to both equations. And last up, we can check a solution by substituting it into each equation to make sure it works in both of them. So let's look at an example. Here I have 2 equations, right? I'm looking for an ordered pair that is a solution to both. So I'm going to do this by graphing. The first equation is nicely already in slope-intercept form. The slope of this line is 4. The y-intercept is negative 11. So I would graph it by putting a dot at, hello. I am sorry, but I'm going to have to fix the board one more time. Let's hope we can get through the entire rest of the notes by this fix. Okay, so the blue line here is going to have a y-intercept at negative 11, and it's going to have a slope of up 4, right 1. Up 4, 1, 2, 3, 4, right 1. 1, 2, 3, 4. I think the more dots you make, the better off you'll be. There is a picture of the answers to the first equation. The second equation is not in slope-intercept form, right? So the first thing I'm going to have to do is I'm going to have to put it in slope-intercept form by getting the y by itself. Divide everything by 2, and I get y equals negative 5 halves x plus 2. So that one has a y-intercept of 2 and a slope of negative 5 over 2. I would put a dot at 2 on the y-axis, and I would go down 5, right 2, down 5, right 2, and I can draw that line. All right, so I have done the first step. I have graphed each equation. The next thing I want to do is I want to do this. I want to name the point where the lines intersect. Obviously, they intersect right here at the green dot. That is an ordered pair that is on both lines, and because it's on both lines, it's a solution to both equations. And that is the ordered pair 2, negative 3. I claim that 2, negative 3 is the solution to this system. All right, let me go over here and check my answer to see if it is. So I'm going to take this first equation and I'm going to rewrite it as negative 3 equals 4 times 2 minus 11. Is that the correct answer? That'd be negative 3 equals 8 minus 11, or negative 3 equals negative 3. It is a solution to the first equation. How about the second equation? Is it a solution for that? So that would be 5 times 2 plus 2 times negative 3 equals 4. Or 10 minus 6 equals 4. And obviously it works for that one too. Because this ordered pair is a solution to both equations, it's a solution to the system. All right? That is your goal. Your goal is to find an ordered pair that works for both equations. And we're doing it by graphing. I have one more thing to show you, and it is this. It is possible for a system to have no solutions. All right, we have a special symbol for no solutions. It looks like this. I think we covered that back in chapter 2 also. So let me show you why this is no solutions. All right, let's go ahead and graph this one. This one is already in slope-intercept form. It's got a y-intercept of positive 4, and it's got a slope here of negative 1. Which means go down 1, right 1. So that line is going to look like this. Now the other equation here is not in slope-intercept form. Oh my gosh, the board is terrible tonight. So I am going to subtract x from both sides. At least I'm going to try to finish this off. This one has a y-intercept of negative 2, and it's got a slope of negative 1 over 1. So I'm going to want to put a dot at the y-intercept, which is negative 2 right there. And the slope is also down 1, right 1. So I'm going to go down 1, right 1. Oop, I'm out of space there. Instead of going down and to the right, I can go up and to the left. Hey. And my line would look something like, that. Notice that these lines do not intersect. That is why there's no solution. And one more thing. Could I have told that there's no solution before I started it? What type of lines are these? That's really my question. What type of lines are these? Well, they are parallel. And lines that are parallel do not cross. And if they don't cross, it means they have no point in common. They have no ordered pair in common. And therefore, when lines are parallel, that is how you know there is no solution. All right, that's it. Good luck on the homework.